So you're a math student? Like, so you teach here? Oh. Okay. Awesome. So I came in as a PhD. I switched for last year, so I don't know if I can say that long.
Morning.
Morning. Need to make money.
Oops, sorry. All right, so let's continue with Neyman-Pearson formulation for detection. Okay, so let me just remind you. The idea here was that we had a vector of data, x, and this had various components, let's say x1, x2, and so on, xn. This is a column vector. And the idea was that we talked about computing some function of this data, L of x, and comparing this to a threshold. If it exceeded the threshold, we choose H1. If it did not exceed the threshold, we choose H0. And the idea here is that this Neyman-Pearson theory is going to tell us how to pick this function L in order for us to realize some optimality criteria. Now, I also want to remind you that this expression, if we look at it, at the point where L of x is equal to the threshold, this thing basically defines a surface, okay? And this defines a surface in some n-dimensional space, and it splits the space into two pieces. And therefore, when you collect this data point, L of x, and you evaluate it, you look at, see where this L of x lands. Does it land to one side or to the other? And according to that, then you make this decision. Okay, other definitions that we made was that the region where L of x exceeds the threshold, we called this the critical region. R1. Now, the reason why it's called R1 is because this is the region where H1 is true. Okay? So we index it with 1, same way. And of course, the region where L of x is less than gamma, this is the region where H0 is true. Okay? Okay, now, given these definitions, we wrote down the expression for the probability of false alarm as the integral over the critical region of the PDF of x, which is the data given h0 dx, and the probability of detection was again the integral over the critical region PDF of x given h1 this time times dx. Okay? So what I want you to note is that for the false alarm, we're integrating the PDF of the joint probability density function for all the data given the H0 hypothesis. For probability of detection, we're integrating the PDF under the H1 hypothesis. Okay. So now the Neyman-Pearson framework is that we want to set this guy here to alpha. We want to fix this to some alpha. Okay, like the example that I used last time, let's say with the fire alarms, you don't want a false alarm more than, let's say, 3 times a year. Okay, so that's this alpha. You fix it. You're the manufacturer, you decide. You fix that. Now what you want to do is, given this fixed alpha, which might be some small number, what you want to do is to come up with a rule defined by L of x that will maximize the probability of detecting an event. For example, a real fire. So this is the setup for the problem. Now how do we solve this problem? Okay, so this is an optimization problem, right? The optimization problem here is that you want to maximize this cost. This is some function. You want to maximize it. And you're maximizing it over R1 subject to a constraint. And the constraint is given by this other equation. Okay? So let me rewrite that. So the optimization problem is choose R1 such that PD is maximized for a fixed PF which is equal to some alpha. Okay? Now how do we do constrained optimization? The most general way to do this is using Lagrange multipliers. And Lagrange multipliers are something that you should know from your earlier studies. But if not, this should count as a little bit of a review. So the way it works is we define a cost function J. This is an aggregate cost function. Listen, would you mind putting that away? This is the second time I've had to ask you. Can you please put it away?
I'm looking at the notes you posted.
What's that?
I'm looking at the notes you posted on cross-referencing what you're saying now with what you said.
You know, I would rather you just put it away, okay? If you need the notes, print them out and bring them to class,
Okay.
okay? No electronics in class, please. Okay, so this is the, we make a cost function which is the probability of detection plus some Lagrange multiplier times probability of false alarm minus alpha. Okay? So this is the thing we want to minimize, we want to maximize, and this is the constraint that we want to satisfy. So we have to solve for lambda here as well, which is the Lagrange multiplier. Okay, so this lambda is a Lagrange multiplier. So let's write this whole thing out using these expressions that we had here. Okay? So this is the integral over R1, PDF of x given h1 dx plus lambda integral over R1 of, well, let me put a bracket around this, PDF of x given h0 dx minus alpha. Okay? All right, now these two terms both involve an integral over dx and over the same region of space, so I can group these two terms together, which is what I'm going to do next. So I write this as the integral over R1 of p of x given h1 plus lambda p of x given h0 dx minus lambda times alpha. Okay? Now remember, what we're trying to do is to maximize this thing over R1. Okay, so now if you look at this, this is the part that we're going to deal with first. This R1 is the region that we have to choose, right? Now, if you look at this expression, it's an integral of two quantities, the sum of two quantities. And what I want to do is to basically just pick R1 in such a way such that this sum is always positive. Okay? In other words, if you look at this integral over this region, the way I get this to be the largest possible, I can't really change anything inside the integral, right? So the only thing I can do is to pick regions of x such that they define an R1 where the integrand is positive. Okay? So what you want to do is to choose R1 such that this quantity here is bigger than 0. Now this quantity is almost always bigger than 0 if lambda is positive, right? Because this is a PDF and that's a PDF. So let's write the condition more explicitly. So you pick R1 to be the set of all x such that p of x given h1 plus lambda p of x given h0 is bigger than 0. This defines the set R1. Okay? Or another way to write the same thing, another way to write this is p of x given h1 divided by p of x given h0 has to be bigger than minus lambda. Okay? Okay? Now, of course, in order for this to be meaningful at all, or to be useful at all, this minus lambda has to be positive, right? Because this left-hand side is the ratio of two probability density functions, so this is positive. In other words, if I pick minus lambda to turn out to be a negative number, that part where this left-hand side is negative is not going to do anything. Okay? So what ends up happening here. Okay. However, minus lambda must be bigger than 0 in order for inequality to be active. And active means, if this thing is negative, then the inequality is not really telling you anything. Okay, so what we do is we define this minus lambda to be some threshold gamma, okay, which is bigger than 0. And so what we have now is, this gives us L of x, which is p of x given h1 divided by p of x given h0 bigger than gamma. This quantity, L of x, which is the ratio of these things, this is called excuse me, the likelihood ratio. Okay? So the bottom line is, Neyman-Pearson test is defined by optimizing this criterion. Going through this, what this shows you is that this criterion is optimized when L of x is the ratio of the two probability density functions compared to a positive threshold. Now, this doesn't tell you yet what the algorithm is for actually computing all of these things, and I'll get to that in just a second. But the other thing I want to point out is that this gamma is not the same gamma that we used last time. Okay? Because the gamma that we used last time, if you remember, took us from minus infinity to infinity along that curve that we call the ROC curve. But this gamma here is always positive. Okay? So this is a little bit different than the gamma we used before, even though I'm unfortunately using the same notation. If you don't like it, you call it gamma prime or whatever you want. All right, so let me summarize what we've done so far in terms of what this whole thing means. So probability of false alarm here, remember, is equal to some alpha. And this is going to be the integral p dx for R1. p dx, we have of x given h0 dx. Okay? So the way this whole thing works is you start with an alpha that you know. Okay, you fix it. That alpha then implies a gamma. Okay? That alpha fixes the gamma. And then this ratio is then compared to that gamma. This is the bottom line behind doing the likelihood ratio test. So let me do a quick example. We'll do many more examples. So if it's not crystal clear right now, that's okay. It will become so. So let's do an example here. Let's say you have two scenarios, H0 and H1. Or under H0, the data x, just a single value is normal, zero mean, variance 1. And under this scenario, it's normal, mean 1, and variance 1. Okay? So, probability of false alarm as a function of gamma is the integral from gamma to infinity, 1 over square root of 2 pi to the minus t squared over 2 dt. Right. This is the q function. Q of gamma is equal to alpha. Right? You're choosing the alpha. Let's say you're setting this alpha to be whatever, 10 to the minus 2. Okay. Then once you have this, then gamma becomes q inverse of alpha. And once you got this gamma, you can take this gamma and stick it in here and do your likelihood ratio test. This will define your overall test. Okay? And we'll do more examples. Okay. So, to summarize, the Neyman-Pearson theorem is to maximize PD for a given probability of false alarm equal to alpha. Use the test Lx equals PDF of x given h1 divided by PDF of x given h0 compared to a threshold h1, h0, where gamma is given by this PDF equals alpha equals the integral L of x given gamma PDF of x given h0 dx. Okay. This test is called the likelihood ratio test. We'll summarize it as LRT. Okay, so next I'm going to do another example. So let me take you through the example, and if it's still not clear, stop me and we'll discuss it further in detail. Okay? Okay. So here's the example. Let's say I have two hypotheses, H0 and H1. Under this hypothesis, the data that I collect is just a bunch of noise samples. And under this hypothesis, the data that I collect is some constant plus noise samples. And here are the conditions. N goes from 1 to capital N, so I have capital N data points. The noise, I'm assuming, is Gaussian with 0 mean and variance sigma squared, and it is independent identically distributed. In other words, the samples of W of N are independent of each other from one N to the next. Okay? Another way to summarize this whole thing, since you have N data points, is you can write for H0, you define a vector X, which is the vector W. W is the collection of all the data, the samples in this Wn here. So this is just the equivalent way of writing this. And then in this case, X is equal to some constant times a vector of 1s plus W. So let me just define these. So X is this X of 1 through X of N. And W is W1 through Wn, capital N. And 1 is a bunch of 1s. 1. Okay? Is the notation clear? Okay. So now the task is, given these N samples, decide whether these samples came from this hypothesis or that hypothesis. Okay? So what we do is likelihood ratio test. We have to do two things. Find the PDF of X given H1, the PDF of X given H0, and then take the ratio of these two, and then compare them to some threshold, right? So now let's do these things explicitly, in detail. Okay, PDF of X given H1. So this is an n-dimensional Gaussian distribution. So the denominator gets a normalization factor 2 pi sigma squared n over 2. And then you have the exponential minus 1/2 x minus a times 1 transpose C inverse times x minus a 1 transpose. Sorry, this transpose goes outside. Okay, this C inverse is the inverse covariance matrix, which in this case happens to be a multiple of identity. So because we had W of n is normal 0 sigma squared, then the vector W is a Gaussian vector random variable with 0 mean and covariance sigma squared times identity. Okay? So this is the covariance matrix inverse of this thing. And PDF of X given H0 is very similar to this, except for the fact that there's no mean, so this A times 1 doesn't exist. So this becomes 1 over 2 pi sigma squared n over 2 exponential minus 1/2 x transpose C inverse x. And again, like I said, this is C. Okay? And now, what we're going to do is to divide these two things. Take that and divide it by this. That's the likelihood ratio. So L of x. If I divide these two, this coefficient in the front here and this coefficient here cancel each other out. So this just becomes a ratio of two exponentials. I'm going to write this in longhand. So this is the exponential minus 1 over 2 sigma squared. This minus 1 over 2 sigma squared comes from the inverse of this covariance matrix times the sum x of n minus a squared. And the denominator, the exponential, minus 1 over 2 sigma squared, the sum of x squared n. Okay, is it clear how I got these two? What I did here is I just multiplied this quadratic form out and I wrote it as a scalar directly. Okay? And the same thing here. So x transpose C inverse x is x transpose times identity times x with a 1 over sigma squared, and that 1 over sigma squared is out here. Okay? Okay, so I could stop here and I could say, okay, well, I'm just going to compare this to some gamma, h1 and h0. And, well, what gamma should I choose here? Well, whatever you want your false alarm to be. Unfortunately, this is a little too messy. Okay? So generally, we don't stop here. What we do, in fact, is we try to simplify this left-hand side as much as possible so that the form of the function L of x becomes simple. You can imagine if you want to do this implementation in a computer and calculating this whole thing and then calculating this whole thing and then exponentiating and dividing, that's a lot of operations. So let's see if we can simplify this thing. So one of the easiest things we can do is actually take logarithms of both sides of this inequality. Now, why can we do logarithm? We can do log because log is a monotonic function. Okay? Therefore, it doesn't change anything about the test if we just take logs of both sides. There are many other monotonic functions that we could use. But we use log because log gets rid of the exponential and simplifies things. Okay? So you take log and you simplify, and what you get is minus 1 over 2 sigma squared sum xn minus a squared plus 1 over 2 sigma squared sum x squared n. Now this is no longer going to be compared to gamma, but rather it's going to be compared to the log of gamma, right? h1 and 0. Does that make sense? Okay. All right, so simplify further still. Let's leave that here for a second. So this quadratic here can be expanded and then simplified. So what you see here is if you expand this quadratic, you're going to get a sum of x squared here. And that's going to get rid of this sum of x squared here. All right, so it's going to get really simple. And what you're going to get is minus 1 over 2 sigma squared minus 2a sum of xn plus n a squared. And this is compared to log of gamma, h1, h0. Okay? All right, then just continue to simplify this and move things around so that the only thing left on one side of the equation are stuff that is related to x of n. So eventually you get an equation like this. Sum of x of n, this is n equals 1 capital N, compared to sigma squared over NA log of gamma plus A over 2. Okay. Now I've chosen to keep this 1 over n on this side. I don't have to. I can move this to the other side as well. Okay. And I can take this whole thing here and just call it another threshold gamma prime. Okay. So what does this tell you? It tells you that in the end, once you've simplified everything, your likelihood ratio test basically turned out to be comparing the average of the samples to a threshold. Even though up here it was this ugly looking expression, once you simplified everything all the way down, then it became just the average compared to a threshold. Okay? Questions? No?
Where is the A squared?
I'm sorry?
There's two formulas. The first one has an A
Did I
squared.
make an algebra mistake here?
No, that looks right.
No, I think it's correct. There's an a squared here because this
yeah.
gets a squared from here. Okay. So one thing I want to point out is that this left-hand side is only a function of the data, right? The right-hand side, however, is not only a function of this gamma, but it's also a function of some parameters. So it's a function of sigma squared, and it's a function of A. What this means is that you're kind of assuming that you know A, right? And you're assuming that you know sigma squared. If you didn't, then the right-hand side wouldn't be well defined. So this kind of gives you an idea that this likelihood ratio test assumes that the parameters of the probability density functions are known. So you get a bunch of random data, but at least the parameters of the PDF must be known. If they're not, we can deal with it, but not yet. Later on in the course, we discover how to deal with those things. Okay, so there's something special that happens here. In other words, this kind of ugly expression ended up giving you something fairly simple. Okay, this quantity is essentially summarizing all the information that you need to make a decision, right? In other words, once you get to this point, you no longer need the individual data points. All you need is their average, right? So if I didn't give you the individual data points, but I only gave you their average, you could still make this decision exactly the same, right? That's kind of a special thing, right? This kind of thing is called a sufficient statistic. Why is it called sufficient statistics? Because knowing this is sufficient for you to make your decision.
This assumes that the likelihood of H0 and H1 is equal, right?
It assumes that we know nothing about the likelihood of H1 and H0.
Oh.
Okay? I haven't said anything about it. It turns out that if you go to the more general situation where you know something about them and then you assume that they're equal, you kind of end up coming back to this. But here, I'm assuming I don't know anything about the prior likelihood of H1 and H0. Okay? So the only thing that drives your decision is the data. Okay, so this is called the sufficient statistic, but more generally, the quantity that you, at the end, once you have simplified, you compare to the threshold, is called a test statistic. So that the test statistic in this case is T of x, which happens to be 1 over n times the sum of x and n. Okay? All right, now let's take a look at what this T of x is. So T of x is, of course, a random variable, right? Is a random variable. Well, it's the average of a bunch of random variables, so it must be a random variable as well. And I'm going to make decisions based on how big T of x is. If it's bigger than some threshold gamma prime, I choose one thing. If it's smaller, I choose another thing. Therefore, I need to know something about the distribution of T of x. Okay? Because I'm not going to make my decision directly based on the individual x's anymore. I'm going to make my decision based on this average quantity. So I might as well, or not I might as well, I have to know what the statistics of T of x are. Okay, so let's find out. So first of all, remember that these x of n's I assumed were Gaussian, right? So when I average the x of n's, I'm going to get another Gaussian. So what I don't know is I don't know the mean and variance of this new Gaussian. So let's figure it out. The expected value of T of x given h0. This is the expected value of 1 over n sum wn. Right? Because when h0 is true, then x, if I go back to the original definition of the hypotheses, when h0 is true, x is just noise. So under this hypothesis, this sum, or this average, becomes just 1 over n times the sum of wn. Okay? And the expected value can just be pushed inside the sum. The expected value of each one of these guys was 0, because it was a Gaussian with 0 mean. Therefore, this is 0. Okay? On the other hand, expected value of T of x given h1 is just a, right? Because x of n is, in that case, it's a plus noise. The noise is 0 mean. You get 1 over n times the sum of a's n times, and the n cancels the n, and you just get a left over.
Right, so I mean, this does tell you the likelihood of h0 and h1. I mean, that's one of the requirements to run this test then.
Nope.
Well,
Where did I assume that I knew h0 and h1? Which one was more
the mean
likely?
of x.
Hmm?
The mean of x. I mean, since x can vary between h0 and h1, the mean will be related to the likelihood of h0 and the likelihood of h1.
I'm not quite sure I'm following you.
Okay, that sum, 1 over n, sum of x of n, that is related to the likelihood of h0 and the likelihood of h1.
No, it's not.
Well, why not?
Because I'm computing that sum under the assumption that h1 is true, and then under the assumption that h0 is true. I'm not saying that one is more likely than the other.
You're running them separate then?
Yeah, I compute this mean under h0, I compute the mean under h1. I didn't say this one was more likely than that one. I'm just saying if this is the case, this is the mean. If this is the case, this is the mean. That's it. Okay? All right, now the variance as well we need to know. Variance of T of x conditioned on h0. This is the variance of 1 over n sum of w of n. So the variance of the sum, because these things are independent, identically distributed, this is 1 over n squared times n sigma squared. So it's sigma squared over n. Okay? Variance of T of x under h1 is the same thing, sigma squared over n, because the only difference is that the constant, the deterministic, non-random constant has been added in the other case. Okay, so the variance is the same. Therefore, under these two hypotheses, h0 and h1, T of x is distributed as a Gaussian with 0 mean and variance sigma squared n. And under this other hypothesis, T of x is Gaussian with mean a and variance sigma squared n. Okay? So all I did is these calculations were simply to come down to this point so that I can know what the statistics of T of x are. Okay? And just going back to the question, I've made no assumptions about h0 or h1 being more likely, one being more likely than the other. I'm just kind of following in parallel the statistics of everything that I compute for the two different hypotheses. Okay? All right, so now remember, I can do the test on T of X, so I can define my probability of false alarm and my probability of detection based on the test statistic T of X. Okay, so let's write down the probability of false alarm. This now is going to be an integral. Well, let me write it as the probability first. Probability of T of X bigger than gamma prime under H0. Okay? This is just going back to this this expression here. Yeah.
Do you mind going back to the last sheet?
That's true.
I'm still
the last sheet.
Okay, so right there where you have the right by the sufficient statistic. So you're taking the mean of a length of the signal and you're comparing that to your gamma prime.
Well, first of all, this is not the signal. This is a measurement.
Okay. The
Okay.
measurement. So you've taken some measurements and then you're comparing them to gamma prime.
I'm comparing the mean to gamma prime. Yes.
Right. Now for those measurements, are they all the same hypothesis, or do they vary between the two, or do they vary between H0 and H1?
They do not vary between H0 and H1.
So they're all the same.
Right. So the point is, I'm trying to decide if all the data came from H0, if all the data came from H1. I'm not assuming that the data, I think I see the source of your confusion. You're thinking each sample might have come from this one or that one. Right?
Right.
Okay, no, that's not what I'm talking about here. I'm saying all the data points came from H0 or all the data points came from H1.
I see. So then it's more. So then that mean is basically just the hypothesis, essentially.
Yeah, well, I mean, that's why it's called the sufficient statistic. The mean tells you everything you need to know.
Yeah.
If the mean is high, it means A was there.
Mm-hmm.
If the mean is low, it means A wasn't there.
Okay.
Okay?
No, it makes sense.
Okay. Now, it's a common confusion to have we're not trying to extract sort of individual labels here by saying, okay, this data point came from H0, this data point came from H1, and then the next one came from the... That's not true. All I'm saying is all the data either came from H0 or all the data came from H1. And I don't know which. Okay? All right, so the probability of false alarm is the probability of T of X exceeding gamma prime given H0. Okay? Now, what I want to point out is this probability description is different than the one that I wrote for you before. Right? This probability of false alarm is written as the probability of T exceeding some threshold. Okay? Before, we talked about the probability of L exceeding some threshold or X itself exceeding some threshold and so on. This is written explicitly as the probability of the test statistics exceeding the threshold. So we can write it like this. This is the integral from gamma prime to infinity, PDF of T of X given H0, now dt. Okay? Or more explicitly, it's the integral from gamma prime to infinity, 1 over square root of 2 pi sigma squared over n, e to the minus t squared over 2 sigma squared over n dt. Okay? I'm using this because this is the distribution from here. Okay? So this is a Gaussian with 0 mean and variance sigma squared over n. This is the integral of this Gaussian from gamma prime to infinity, which is the definition of the false alarm. Okay, so this integral here is the Q function, Q of gamma prime over square root of sigma squared over n, and this is equal to alpha. Okay, so if you want to figure out what your gamma prime is for a particular alpha, you just have to invert this equation. You do Q inverse and then you solve for gamma prime. Okay. Similarly, The probability of detection is again integral from gamma prime to infinity. Remember, this gamma prime to infinity here is the R1. Okay? One of the advantages of writing the probabilities in terms of T of x, the test statistic, is that now you can just deal with something that's one-dimensional. Right? You don't have to think about R1 as a region in high-dimensional space. You've collapsed everything to a scalar. Right? So that makes it a little simpler to look at. So this is PDF of T of x. Sorry, let me just write the 2 pi sigma squared over n. This time it's exponential. It's very similar to the one before, except that it's minus t minus a squared over 2 sigma squared over n dt. Okay, and then we write this again as a q function. It's q gamma prime minus a divided by the square root of sigma squared over n. Okay, so this was the false alarm. It's a function of gamma prime, and this is the PD as a function of gamma prime. Okay? Okay, so now if I wanted to characterize the gamma prime from here, I could say, well, I take this guy here, and I rewrite it. I get gamma prime equals square root of sigma squared over n times q inverse of pf. Okay? And then this gamma prime gets plugged in to here to give me the corresponding probability of detection. Okay? So PD becomes q of, then this thing goes in place of this gamma prime. Square root of sigma squared over n, q inverse pf minus a divided by the square root of sigma squared over n. Okay? So what does this tell me? This is just going to give me a curve, right? PD versus PF is going to give me something like this. That's 1. That's 1. This is PD. This is PF. Okay? Now, generally, you won't be able to write an equation in closed form like this. I mean, this is kind of closed form, even though it has this Q function. Generally, what you will do is you will compute the false alarm if you want to plot this curve. You will compute the false alarm for every value of alpha from 0 to 1. For every value of alpha, you will solve numerically, and you will get a gamma prime. Then numerically, you will take the gamma prime and plug it into this equation and compute the corresponding PD. Therefore, you will get the points on this curve one at a time. Okay? This you can do in MATLAB in one line. Okay? In general, that won't be possible. In general, you'll have to have a for loop that spans through all the values of alpha, gives you the corresponding gamma. That gamma will get plugged into this integral. The integral will get computed numerically, and then you'll get 1 point. And then the next k equals 2, you'll do this all over again. Okay? In a for loop. In special cases, when the hypotheses are very simple like this, and you have a Gaussian against another Gaussian, then the calculations are simple. But this thing in particular here can be simplified a little bit more. In fact, this sigma squared and this sigma squared can cancel each other out, right? So what you end up getting is an even simpler form. You get PD is Q inverse PF minus, then I'm just going to gather everything together, N A squared over sigma squared. Okay? So actually you can completely specify the performance for any false alarm. You can specify the performance just using this term. Okay? In fact, this term here happens to be known as the signal to noise ratio. If you had a single sample, x of n, then the signal to noise ratio would be a squared over n squared. That's the amplitude of the signal. This is essentially the variance of the noise. The ratio of those two determines the performance of the whole thing. Now, instead of just one sample, you have n independent samples. Therefore, the signal to noise ratio is boosted by a factor of n. Okay? So if you plot this whole thing as a function of different signal to noise ratios, what you will get is this curve. You might get something like this for a particular value of n, and if you had a higher signal to noise ratio, your detector might behave like this. Okay? So the idea here is that with higher signal to noise ratio, your curve moves up like that. Higher signal to noise ratio. Now it's interesting to look at the signal to noise ratio and notice that there's several different ways in which the signal to noise ratio can be boosted. One of them is, of course, n, right? If you continue to capture more and more samples, your signal to noise ratio improves. Okay? Another way to do it is to boost a squared. Excuse me?
That burns power.
That's right, that burns power. So that's something you don't want to do necessarily. Okay? The other thing you can do is squeeze sigma squared to a smaller number. Okay? So there's various things you can do here. N is time, right? So this is called integration time. If you want to get the signal better, if you want to get a better decision, you just wait longer. You keep integrating the data, means you keep measuring more data points. If you can't do that, then you have to either boost your power, right, boost the signal, or make sure that the noise is smaller. Oftentimes you don't really have much control over sigma squared here, because it's determined by either the circuitry or the channel over which you're communicating. There's not much you can do here. So you either boost power or you measure more samples. Now it turns out this particular property is true when the samples that you're collecting are all independent. Okay? But what would happen if the samples, x1, x2, x3, and so on, they were actually correlated to each other? It turns out that the effect on the signal to noise ratio is a little bit more subtle. And we'll get to that in another example later. But these are all things worth thinking about. Okay. Now, again, just to emphasize the point, things almost never turn out this simple. Okay? So you essentially always have to keep, you set a false alarm rate, you compute your threshold, you put your threshold into the integral for PD, and then you compute that, and then you plot the curve. There are many, many examples of that. There are more examples of that than simple cases like this. Okay, so related to this idea, there is something worth mentioning here. This is called the Neyman-Pearson factorization theorem. Okay, so this is related to the sufficient statistic that we just talked about. Suppose that under H0, the PDF of x given H0 could be written in terms of a parameter, which is P of x, let's call it theta 0. Okay? So for instance, in our case, the theta 0 here was A and sigma squared. Right? Those are the two parameters that define this guy. Well, not here it was just sigma squared. H1, P of x given H1, and P of x given theta 1. Okay? Okay, so sometimes it is possible to factor this guy in a form that will allow you to write it as a product of two pieces. So if you can write P of x given theta I, and this is I equals 0 and 1, as some function g of t of x given theta I times some other function h of x, then what happens is that the likelihood ratio becomes g of t of x given theta 1 times h of x, and g of t of x given theta 0 times h of x. Okay, so what happens here is that this h of x and this h of x cancel each other out, and you get a simpler ratio. When this is happening, this t of x is precisely what I showed you earlier as the sufficient statistic. So what I'm writing here is a kind of more abstract form of what you saw earlier, which was when things cancel out. Okay? When the likelihood ratio can be simplified so that the whole thing can be written as another function t of x in simpler form, that t of x is called the sufficient statistic. And this factorization theorem simply says if you can write this p of x in this form, then what's left over inside this g of t of x is necessarily the sufficient statistic. In other words, you don't need the actual samples anymore. All you need is a summary of the samples as given to you by t of x. Okay? So this is just a general simplification result. Okay, so now let's go back and talk a little bit more about this receiver operating curve, which we've discussed before. This is the ROC curve. Okay, so as I said, these ROC curves typically look like this. And this value is 1. This value is 1. Okay? And any point on this curve is basically a parametric equation. You have PF of gamma and PD of gamma, or gamma prime, whatever you happen to be using. And whenever you have a stronger signal or less noise, then this curve will just move up. So what is the ideal receiver operating characteristic? What is the best ROC curve you can have? Is this. Okay? And what does that mean? It means for any false alarm rate, you get perfect detection. Okay? On the other hand, you have this curve that we talked about last time, which was the so-called chance line. So let me draw that on a separate plot. So this is the chance line. Okay, this is at 45-degree angle. Okay, so how do we get this chance line? As I mentioned to you, this is just coin tossing. So let's do it like this. So if you toss a coin, and if you get heads, you choose H1. And if you get tails, you choose H0. Okay? Now let's compute the PD and PF for this, just for fun. Okay? What's the probability of getting heads under H0? Well, the probability of getting heads is independent of H0. Right? It's got nothing to do with H0. It's just a coin you're tossing. Right? So this is just the probability of heads, which we can call P. PD is probability of getting heads given H1. And what's that? Again, same thing. The tossing of the coin has nothing to do with whether H1 or H0 is true. So that's also P. So what happens? PF and PD are always P. So they're equal to each other. Therefore, they're on a line of 45-degree angle. Okay. Now that part is not too surprising. The part that's a little bit more surprising is that you actually don't need a fair coin even. Okay? I didn't tell you this P was from a fair coin. Right? So pick any coin that has nothing to do with the hypothesis and just flip it. And you'll get this curve. Okay? That part, at least to me, it's surprising. Right? You don't need a fair coin in order to get the chancellor. That's a little weird, but it's true. Okay. There are many, many properties, many very interesting properties that these ROC curves have, which we have to discuss. All right, so let's talk about the shape of the ROC curve. You notice, so far, I have always written, or I have always drawn the PF, PD ROC curves like this. Right? Well, you might say, how about this? How come it can't look like this? Okay. Now, it turns out that ROC curves that you get from any kind of likelihood ratio test, like we've talked about so far, always have to look like this. This is okay. This is not okay. ROC curves computed from test statistics that are based on a likelihood ratio can never look like that. We will talk about why in a moment. But the point is, if you in fact solve a problem and I ask you to compute the ROC curve, and you go ahead and you compute the ROC curve, and the test that you've designed is based on a likelihood ratio test, and you get a ROC curve that looks like this, go back and do it over again, because you've done it wrong. Okay? All right, so let's analyze the shape of this ROC curve in a few different ways. First of all, let's take a look at the slope of the ROC curve. So this is just a curve, right? So at any point I can pick a point, and then I can look at the tangent and the slope. Let's see what the tangent looks like. So the slope is going to be d PD dPF, right? It's just the derivative. Okay, now I can write this as dPd by d gamma prime dPf by d gamma prime. Okay? I can just write it as a derivative, and this d gamma prime basically cancels out, essentially, right? Okay, so now remember that Pf is the integral from gamma prime to infinity of P of t given H0 dt, and Pd, integral of gamma prime to infinity P of t given H1 dt. Right? Okay. Now, given these two, what's the derivative of PD with respect to gamma prime and the PF with respect to gamma prime? That's just taking the derivative of this integral, right? If you take the derivative of this integral, what do you get? You get the integrand evaluated at the endpoints, right? Just the fundamental theorem of calculus. Now, P of t given H0 at infinity, we're going to assume that's 0. We're going to assume that the PDF dies out, right? So it's not big at infinity. Same here. Okay? Therefore, this ratio, dPd dPf, becomes minus P at t equals gamma prime given H1 divided by minus P t equals gamma prime given H0. Okay, and this minus just cancels the minus. Okay? Now I have a ratio of two things. Right? These two things are the PDF for t evaluated at gamma prime under H1 and PDF of t evaluated at gamma prime given H0. These two things are just PDFs. They're both positive. Right? So therefore, this guy, this ratio, always has to be positive. Okay? So what have I just shown you? I've proved to you that the slope of this curve, as long as you have something that comes from a likelihood ratio test, the slope of the ROC curve always has to be positive. Okay? Yeah.
Isn't the PDF of t equals gamma prime 0?
I'm sorry, say that again?
Isn't that PDF of t equals gamma prime, regardless if it's H1 or H0? Doesn't that PDF equal 0?
No.
Why not?
Because I'm just evaluating the PDF for a particular value. I'm not looking at the probability. This is not a probability. This is the PDF. Okay, so you can plot the PDF and then look at the value of the PDF at a particular point. Okay, so the point, what I'm trying to show you is that the slope is always positive, right? So it's kind of, got to look like this. Okay. And there are many, many other properties which we will get to in due time. But what I want to do is now talk about, in the remainder of the time, a very specific case of the detection when we now have some information about how likely each one of these hypotheses are. And that's going to be related to, okay, so let me go back to this. The ROC curve for likelihood ratio tests characterizes the performance for any false alarm, right? So if you choose your false alarm to be really small, here, then you're operating at this point, right? If you choose your false alarm to be bigger, then you're operating at this point. Just like when you plot the voltage current curve for a device, you pick an operating point, right? And you turn your device on at that operating point. Here's the same thing. You have your detection system, and you're going to set an operating point. Sometimes it's nice to have kind of automatically figure out what the best operating point is. So this is a discussion we had in the first lecture. Well, what about a case where somehow the sum of the false alarm and the detection is optimized, right? Together. Let's see what happens there. So this is called the minimum probability of error signal detection. Okay, so far we ignored the probability of H0 and the probability of H1, right? So just to be clear, whenever I'm talking about a PDF, I'm going to use P of something, a little p of something, and whenever I'm talking about probability, I'll write it as PR. Okay? Okay. Now, in general, these two things are not equal, right? So there's some weight that you have to give to one hypothesis versus the other. Okay, so there's a so-called Bayesian approach which allows us to take into account information about these two things. What we can do is to define an overall probability of error. And we summarize this by writing it as P sub E. So what's the probability of error? Well, remember we had two different kinds of errors we could make, right? So let me write the probability of error as probability of picking H0 and H1 being true, plus the probability of picking H1 and H0 being true. Right? These were the two different kinds of errors that we made. Okay? I can now write these two in a slightly different way. I'm going to use conditional probabilities to write these now. So the first one is the probability of picking H0 given that H1 is true, times the probability of H1 being true, plus the probability of picking H1 given H0 is true, times the probability of H0. Okay? So these are AND statements. I change that to a conditional statement, and then I have to multiply it by the conditional, by the prior probability of this one being true or the other one being true. Right? Okay. These two quantities are quantities we've studied before. In fact, we just studied them. What's the probability of picking H1 when H0 is true? What did we call that just a minute ago? That's the false alarm, right? Okay, so this is probability of false alarm. What about this one? Picking H0 when H1 is true. We call that missed detection, right? Okay, so this was probability of missed detection. So to summarize, I can write the probability of error as probability of missed detection times, let me call this guy P0, and let me call this guy 1 minus P0, right? Because they sum up to 1. So PM times 1 minus P0 plus PF times P0. Okay? Let me rewrite this a little bit differently. Okay, I don't want to keep carrying around PM because the thing that we use is probability of detection. Okay? So what I'm going to do is I'm going to write probability of error as a function of gamma now. This is a threshold, right? You can write it as gamma or gamma prime, doesn't matter. This is equal to P0 times the probability of false alarm as a function of gamma plus 1 minus P0 times 1 minus probability of detection as a function of gamma. Right? Okay. So the thing that I can control here is my threshold gamma. So I want to choose a threshold in such a way that the probability of error is as small as possible. So what do? I differentiate this with respect to gamma. Set it equal to 0, find the solution. So dPe gamma, d gamma. Now I differentiate. This is P0 times dPf d gamma plus 1 minus P0 times minus 1 dPd d gamma. And I set this equal to 0. Okay? Then you simplify. The dPd d gamma divided by dPf d gamma is equal to P0 over 1 minus P0. Okay? And remember, this I can also write as dPd dPf. Right? So what does this do? This tells me, remember what this was. Right? This is the slope of the ROC curve. Right? So what does this tell me? It tells me my operating point is going to be where the slope of the ROC curve is equal to the ratio of the two probabilities that I have ahead of time. Okay? It's a beautifully simple result. It says take the ratio of the two probabilities that you have and that gives you the slope, and go along this curve, and because we know that it's convex, there's only one point that's going to have exactly that slope, and that's going to be your operating point. That immediately tells you what the threshold has to be, it tells you what your false alarm is going to be, it tells you what your detection probability is going to be. Okay, so sort of graphically speaking, here's the curve. 1, 0, 1. Okay, let's take an example. Suppose that ahead of time, our probabilities were equal, right? Suppose probability of H0 and probability of H1 were both 1/2. So what would happen? You would have 1/2 divided by 1/2 here. The slope would be equal to 1. So what you would get is you would get a line at 45-degree angle, which is parallel to the chance line. Remember I told you a couple lectures ago you would get that line, and now I've shown you how. Okay, so you would get this point, for example, here. And that happens to be parallel to this for P0 equal to 1/2. Okay? Any questions about this? No? No questions? Okay. All right, so let me, in the time left, let me do one more property of the ROC curve, which again is kind of surprising. There are many things that are surprising about this ROC curve business. Okay, so what I want to talk to you about is something called a randomized test. Okay, so here's the idea. What you're going to do is you're going to take 2 points in this space, PF and PD, and say I take a point here and I take a point here. Okay? Let's say this point is PF of gamma 1, PD gamma 1, and then this point is PF gamma 2, PD gamma 2. Okay? And now, what I'm going to do is I'm going to define a parameter alpha, which goes between 0 and 1. Okay? And I'm going to write the probability of getting, okay, so I'm going to define a test which works as follows. You imagine that you have a coin, okay, which has probability of heads of getting alpha, alpha probability of getting heads, and 1 minus alpha probability of getting tails, okay? Then, what I'm going to do is I'm going to flip this coin. If it comes up heads, I use this threshold. If it comes up tails, I use this threshold, okay? In other words, I have not decided what my operating point is going to be. Okay? So what I do is I randomly choose an operating point. And the way I do it is so you have a coin with probability of heads equals alpha, and probability of tails equals 1 minus alpha. So if alpha, if heads happens, you use gamma equals gamma 1. Otherwise, use gamma equals gamma 2. Okay? All right, now let's assume also that, these points here are from some likelihood ratio test, right? Just like we said before. Okay, now, if I did this, what would happen to the probability of false alarm and the probability of detection? Well, probability of probability of false alarm, let's call it PF star, would be alpha times the probability of false alarm, gamma 1, plus 1 minus alpha, probability of false alarm of gamma 2. Right? And probability detection star would be alpha, probability of detection, gamma 1, plus 1 minus alpha, probability of detection, gamma 2. Does this make sense? The reason why this happens is because I am randomly choosing between these points. And so with probability alpha, I'm going to get this false alarm. With probability 1 minus alpha, I'm going to get this false alarm. Right? So the false alarm effectively is going to be the weighted average of these two. And same is true for the probability of detection. Okay, now what does this mean? What this means is that the PF star and PD star are actually going to live along the line connecting these 2 points. Okay? These two, in fact, define all the points along this line. So PF star, PD star is somewhere along this line. Okay? All right. Why did we bother with all of this? The reason why we bothered with it is because if you remember earlier when I said that curves have to be convex, right? What's the definition of a curve being convex? Okay, just the geometric definition of a curve being convex. The definition is that if I pick any 2 points and connect them with a straight line, the curve always has to be on the same side of that line, right? Now look at this. What this says is that the ROC curve that I draw always has to be above any line connecting the 2 points. Okay? So what it means is that the ROC curve has to look, something like that. Okay? Now let me mention one last thing, which is suppose that I had a ROC curve that didn't satisfy this condition. Suppose I had a ROC curve that did this. Okay? Now, if I take a line that connects these two points, and I do this, I can achieve performance along this line by simply randomly choosing between these 2 points. Right? So if my ROC curve was not convex, I could always flip a coin and make it convex. Okay? So I would pick 2 points along the convex parts of this and connect them with a line. This curve here that I get is called the convex halt now. Okay? So the idea is a randomized test will improve on any detector that does not have a convex ROC curve. Okay? So if somebody shows you a ROC curve that is not convex, and you're at a conference and something, immediately raise your hand and say, I can do better. And how do you do better? You pick 2 points, you flip a coin, and you choose between them, and immediately you connect these 2 points with that line. That becomes your new detector. There is no reason why you should have to settle for a detector that has this kind of weird behavior. Yeah?
So, is this effectively adding hysteresis to the detector?
I don't know what you mean by hysteresis.
It's a way of varying the threshold depending on which state you're in.
Well, that's exactly what this is doing. If you want to call that hysteresis, I mean, definition of hysteresis is something different.
Something that the person passed samples.
Well, what it's basically doing is, this particular detector is defective at this point, right, between these two thresholds. It's doing something bad, okay? It's not being very smart. And what this does is it says, because you already have 2 points that are doing okay, you can use those 2 points and ignore everything in between. Right? So essentially what this tells you is that ignore this detector in between and only operate either here or here by random choice. And by virtue of doing that, then you actually close this line and you make it convex. Okay?
I see.
There's no reason why your operating point should have to be in this region. You just move it up. Okay? All right, so this is kind of an interesting idea, and of all the stuff that we've talked about so far, this business of randomized tests is probably the least easy to internalize, right? It takes a little practice, but we'll say a little bit more next time about the ROC curve and its properties, but there's a tremendous amount of information that is buried inside this ROC curve, and a lot of properties that will tell you, what you can get out of it. For instance, it turns out that the slope is actually equal to the threshold at any point on the ROC curve. Right? You saw that before, right? So you saw that the slope was equal to the ratio of these two, P0 over 1 minus P0. It turns out for a likelihood ratio, that's generally true. Okay? Now remember, we had the ROC curve, the threshold here was gamma, and gamma was infinity and minus infinity, right? Okay, those are the slopes. Okay, so that makes a lot of sense when you think about the geometry of the curve as well. Okay, so any other questions? By the way, I emailed all of you about the recordings for the course. Were you able to access them, or did anybody check? You did. Okay, so they're all there, right? Okay. All right, that's it. So I will have your homeworks done a little later today. They will be sitting in a box outside my office, so feel free to stop by and pick them up. Okay?